We are now going to discuss the application and transport layers, the two top layers of the TCP/IP protocol stack. So basically the application layer is responsible for running applications, and it is the same layer which interacts with users. Now the primary protocol which runs at the application layer is the HTTP protocol, which is used to access the World Wide Web or the internet that we know. Now every web page on the internet is made up of objects. Now what is an object? An object is anything which is an image, a text field, a video file. So basically anything that you see on a web page is an object. So a web page is basically an HTML page with different objects. So for example, if we have this page, which is the home page of Google. Now this is the URL, also called Universal Resource Locator, and this uniquely identifies each web page on the internet. And then everything you see on the page, for example, this Google logo, this search bar, or these buttons, all of these are objects. So every web page is basically built up of objects. Now the most popular protocol at the application layer is the HTTP protocol, which stands for Hypertext Transfer Protocol. Now this is the protocol which is used for web browsing. This is the protocol which fetches web pages and renders them onto your browser so that you can see and browse web pages. So basically what it does is that it fetches the HTML file and all the objects within the HTML file, and together the HTML code and the objects on that page, they make up the web page. It uses the reliable TCP protocol on the transport layer. As we previously discussed, all of the protocols on the application layer, they need the help of the transport layer for actual delivery of data between applications. So in this case, HTTP uses the TCP protocol on the transport layer. Now, something special about the TCP protocol is that it is a reliable protocol, which means that if you ask it to fetch 100 objects, it is going to fetch each and every single object. And if there is a problem such as a packet loss or an object got lost, then TCP is going to make sure that that request is sent again and the object is retrieved. Take an example. Suppose you're sitting on your system and running Google Chrome browser, and you want to go to Google homepage. Now the Google's homepage resides on a web server. So what you do is that you create an HTTP request and you send it to the web server. The web server is going to fetch the web page along with all the objects and send them back to you. And that's how the web page is rendered on your browser. So basically at the back end, every time you're browsing a new web page, you send an HTTP request, and in the HTTP response, the web server puts all the objects of that page along with the HTML code, and then this HTML code and the objects are rendered onto your browser and you see the web page. Next, we're going to have a look at the transport layer and how it helps the application layer in delivering data between end systems. Perhaps the most popular protocol at the transport layer is the TCP protocol. TCP stands for Transmission Control Protocol, and this protocol is widely used for web browsing, file transfers, emails. So any application layer protocol such as the HTTP, which is used for web browsing, it basically asks the TCP protocol to do the heavy lifting. Some of the important properties of the TCP protocol is that, first of all, it's reliable, which means that each and every single packet that is sent using the TCP protocol is acknowledged. And if an acknowledgement is not received within a certain span of time, then the packet is resent. So this makes sure that every single packet is delivered. Another important aspect of TCP is that it ensures ordered delivery. As we are going to see briefly, sometimes when you send packets on the internet, say you send packet 1, 2, 3, due to the packets taking different routes on the internet, because the internet is not static, the traffic is changing all the time, and sometimes your packets can take different routes based on if there is less congestion in certain segments of the network. So what can happen is that you can receive packets which are out of order at the destination. So for example, if you sent 1 to 3, you may receive 3 to 1. Now it is the job of the TCP protocol at the destination to reorder these packets before delivering them to the upper layer, which is the application layer. The third point which we want to emphasize is that TCP is widely used for email, banking, downloads. So basically the key property of TCP is that it can tolerate delay, because if you send a packet and you don't receive an acknowledgement and you resend the packet, that introduces delay, but that's fine because the primary motivation of TCP is to avoid loss. TCP cannot tolerate loss. It can tolerate delay but not loss. For example, if you send an email, you want your email to be delivered completely. You don't want some portions of your email or a file that you're downloading from the internet missing. So that's why TCP is very popular for any kind of delivery which needs 100% reliability. In this example, we have HTTP protocol at the application layer and TCP protocol at the transport layer, and we want to send a couple of packets from this system to the destination system over the public internet. Now what happens is that you send packet 1 and you receive an acknowledgement for packet 1. Then you send packet 2, but for some reason it doesn't get delivered and it gets lost on the internet. And this is something which happens a lot of the time due to several reasons. For example, the packet can get corrupted, or it can get dropped on one of the routers on the internet because the router's buffer was full, or a number of 100 different things which can go wrong. But in this case, we don't receive an acknowledgement. So after waiting for some time, the TCP is going to think something happened to my packet too. So what it's going to do is that it's going to resend that packet and keep on resending it until it receives an acknowledgement. So now we have received acknowledgement for both packet 1 and packet 2, and this is how TCP ensures reliability. Let's discuss UDP, the second major protocol at the transport layer after TCP. So UDP stands for User Datagram Protocol. It's widely used in multimedia communication. And the fundamental difference between UDP and TCP is that while TCP offered reliable delivery, UDP is completely unreliable and unordered. So there is no acknowledgement, losses are acceptable, and if packets arrive out of order at the destination, that's fine with UDP. At a first glance, this may seem counterintuitive. However, UDP has a particular use case. It's ideal for multimedia communications. Because you see, in multimedia communications, say you're sending a video from system A to system B. And what's a video? It's a sequence of images or frames which are moved very quickly. So say 1 second of a video has 60 frames. So you need to send 60 frames in 60 packets, let's say. So now if you send 60 packets for that 1 second of video and one of the pictures or one of the frames gets lost, it wouldn't make any difference at the destination, because as for human eyes, it's almost impossible to detect any difference between a video which has all those 60 frames versus a video which has 59, 58, or let's say 50 frames. So that's why it doesn't really matter if you have a few losses in UDP. The key point is that data should be transmitted very quickly. That's the fundamental requirement. It's not that you shouldn't have any losses like TCP. Another important point is that, say, even if a packet is lost and you want to resend it in UDP, what would you do? Because you have to wait for that packet to be sent and then acknowledged, and then would you send the next video frames? That doesn't make any sense. So that's why for live streamings, for audio streamings, we always use UDP. It's also used for audio calls that you place over the internet, because again, in your audio stream or your voice communication, even if a few packets are lost here and there, it doesn't really matter. What matters is the speed with which your data is delivered to the destination. So likewise, if we take the same example and instead of TCP we take UDP, the thing that matters is that the speed. Even if there are few losses on the way to the destination, it doesn't matter. We do gain the advantage of a very high speed for UDP as compared to the TCP. Let's have a look at the header of the TCP and UDP protocols. So this is the transport layer header. If you see the two headers, you can note the difference that in UDP we don't have the sequence number and the acknowledgement number, whereas we have these fields in the TCP header. And the reason is quite simple. TCP needs these fields to keep track of its packets. So when it sends a packet, say with sequence number 20, it expects an acknowledgement packet with the sequence number 20 for that particular packet. In UDP, we don't need any acknowledgements and packet losses are fine. That's why we don't have any sequence numbers or acknowledgement numbers. And that also tells us that the UDP header is slightly smaller than the TCP header because it does not have these additional fields. Apart from these, we have the source port and the destination ports. And this is something which is related to sockets. So globally speaking, the fundamental differences between TCP and UDP need to be explored in detail. It's very important that you understand the fundamental differences between TCP and UDP and where to use which protocol. So TCP offers reliable delivery using the mechanism of acknowledgements. On the other hand, UDP offers unreliable delivery and there is no acknowledgement. In TCP, if your packets arrive out of order at the destination, they are reordered before being delivered to the application layer. In contrast, UDP does not care about packets arriving out of order and delivers them as they are. Perhaps a very important difference between the two protocols is that TCP is slow and UDP is fast. That's why UDP is ideal for multimedia communication. It's not ideal for example, file transfers. On the other hand, TCP is ideal for things like bank applications, downloads, chat messages, forums, whereas UDP is ideal for live streams, audio chats, video chats. So as a rule of thumb, if you're talking about multimedia communication, normally you'll use UDP. There are exceptions. We can use TCP and we do use TCP sometimes for multimedia as well, but that's the exception, not the norm. So usually for reliable delivery in any application in which we need absolute reliability of the delivery of packets, you use TCP. If you need multimedia, you use UDP. Sockets and ports are important concepts that you need to understand at the transport layer. So basically, consider this example. We have two systems. The first system has an IP of 1.1.1.1 and you need to send some data to a destination system with an IP of 2.2.2.2. Now what happens is that on every system you can have multiple applications running, but every application on a system needs an anchoring point, a kind of a door through which it can send and receive data to the transport layer. So for example, if you have Skype running both on system A and the destination system B, then the Skype application is going to communicate with the transport layer at both ends through special doors or anchors called ports. Now what's a port? You can consider a port as kind of a door, and every application running on a system needs its own particular unique port. Two applications cannot share a single port. So for every application running on a system, you'll have a separate port. Now, if you want to communicate, what happens is that Skype is going to send its data through this port to the transport layer, which is going to deliver it to the destination transport layer, and then the transport layer is again going to use this port to deliver this data to the corresponding Skype application. Always remember that socket communication is bidirectional. So if you're sending data on socket in one direction, you can also receive it. If you have another application running on different ports, then you can obviously have multiple concurrent communications. But always remember, every application will have its own unique port. Now we come to the concept of socket. It's kind of the same concept as the port with just one additional caveat, and that's the IP address. So what's a socket? A socket is IP plus port. So for example, if you're sitting anywhere in the world and you want to send data to this Skype application running on this particular system, then you need to use the IP of this system so that your packet can be routed to this system, and then the port 2003 in this system so that the transport layer knows where to deliver the data. So when you combine the IP and the port, this means that your application is addressable anywhere in the world. If you know the IP and the port, you can send your data to that destination application, be it anywhere in the world. Now port numbers are always stored in 16 bits, which basically means that you can have 2 raised to the power 16, roughly 65,000 different ports. And since we just discussed that every application needs its own unique port, so theoretically every system or every PC can support 65,000 different applications at one time. So another question is that, say, if we know the port of a application, is that enough? For example, if we say that we want to go to a Skype running on port 2000, is that enough? Certainly not. We absolutely need the IP address as well, because we don't know the computer where to go. So it's only when you combine the IP address and the port, which basically translates to a socket, only then you can deliver your data to the actual application running on a particular system. Ports have ranges. Ports are divided into two parts. The first 1000 ports are called reserved ports. So the first 1K ports are called reserved ports and the remaining are called unreserved ports. So what are reserved ports? Reserved ports are ports on which we have well-known servers running. So for example, if there is a system and there's a web server running on it, then we absolutely know that it will always run on port 80. This is fixed. Similarly, if you have a file server running, it will be using port 21. If there's an SMTP server running for handling emails, it will always run on port 25. Consider it this way. So you're sitting on your browser and you want to access a web server, let's say Google web server, and you know the IP address of that machine, but you don't know which port on that is that service running. So you don't need to guess it. So the first 1000 ports are reserved and the rest are free. So for example, if you're writing your own socket application, you're more than welcome to use them. This concludes our lecture. I'll see you in the next one.